This is the second video from Cyclic Voltammetry. In our last session, we have seen how Nernst equation determines the uh, concentration of the constituent ions in the bulk material, that is from the electrolyte. In electrolyte, how the concentration of ions varies as a function of the potential. So this is the Nernst equation. This is the applied voltage. This is the redox potential of the material. And F, the Faraday's constant. R is the universal gas constant. T, the temperature. Fc is the concentration of oxidized ions. This is reduced ions. This is the cyclic voltammetry curve, and E half. This E half is determined from the curve. Now this is the redox potential. Redox potential of the material. Now let us see how we can find the redox potential from the curve. Now here there are two peaks here. One is occurring at the point C, that is Fc plus is reduced to Fc by accepting an electron. So here is the reduction occurring, and when the cyclic voltammetry is reversed, or the potential is reversed after reaching the point D, a point is reached where there is a point F. This is where Fc ions becomes Fc plus and electron, that is the Fc is losing an electron. This is where oxidation takes place. Now here we have potential at Fc. So potential at C is Vc, and the potential at F is Vf, and if we divide by 2, it gives us E half. So E half is the half of the potential, sum of the, or the average potential of C and F, the redox and oxidation. Oxidation and reduction peak. This is also called the formal potential, which is given as E half. Now what does this Nernst equation do? Nernst equation will predict how the system will respond to change of concentration and as well as the change in electrode potential with respect to the change in concentration and also the electrode potential, how the system will change. That means if there is a change in electrode potential, the concentration will change, and if there is change in concentration, the electrode potential will change. Now this is the potential if that E, that is the applied voltage, is that we are going to apply applied voltage to the electrode. if that is equal to E naught dash. That was the our standard potential, which is, this is the standard potential. And if this is equal to E half, that is derived from the graph. To our system in the Fc plus solution, that means the solution containing Fc plus, the Nernst equation predicts that Fc plus will be reduced to EFC until this concentration becomes equal. That means in any system, that means in any electrolyte, the system will be tending towards to make this concentration equal, so that equilibrium is achieved. That equilibrium will be achieved only when the concentration of the Fc plus and the concentration of the Fc remains same. That means it should be 50% of the Fc plus and 50% of the Fc. That means both are in equal concentrations. Now when a solution of Fc plus is scanned to negative potential, that means our electrode is in the beginning is at high potential, high positive potential. So from high positive potential we are scanning towards or moving towards negative potential. That means we are applying the electric field, that is our material Fc. This is this will be our electrode, and this electrode, when we give negative potential, it will leave out the electron, and this electron left will be accepted by the Fc plus. So when we give negative potential, that means as and when we start giving the negative towards the negative, that means from positive 0.3 towards the minus 0.3, we apply a negative potential in this way, and we can see that it's up to for example up to maybe around 0.1, there is no change in the current. The current is almost the constant. Now as and when it reaches 0.1, the current starts to increase. That means at this point where this reduction is taking place, that means Fc plus is getting reduced. So here Fc plus is reduced to Fc at the electrode. That means when there is an electrode here, on this electrode, from the electrolyte Fc plus will, so electron will be on the surface of the electrode, so Fc plus will get attached to this electron, because from in the electrolyte electron cannot move in the electrolyte, so Fc plus in the electrolyte requires to move towards this electron so that it get accepted, and it will stay this and it will become Fc, and on becoming Fc it will stay on the electrode. Now this is why our electrolyte should be ionically conducting, so that the ions can conduct more faster, quicker, so that the current can be higher. So this is what happens at the electrode, and the resulting measurement of current and the depletion of Fc at the electrode. So this is what happens, that is this reduction of Fc to Fc plus, there will be a measurement of current, that is this one, this peak will be shown, and there is also a depletion of Fc at the electrode. Now what is this meaning of depletion of Fc at the electrode? Now this is not Fc, this is Fc plus. So Fc plus at the electrode. Now what is happens now in the electrode? Let us take this case. See, this is our electrode, and near this region there will be Fc plus. Now when this Fc plus becomes Fc, there will be less number of Fc plus. There is a reduction in Fc plus and there is an increase in Fc. So this reduction in Fc plus is what is mentioned here as the depletion of Fc plus at the electrode surface. Now this is again the Nernst equation, which says E is equal to E naught dash plus such and such, and then here you have the concentration of Fc plus divided by the concentration of EFC. Now as and when you increase the decrease the voltage, you are moving from positive to negative potential. As and when you decrease the potential to minus 0.3 or somewhere here at 0, this is actually there is a depletion of what? Fc plus. So Fc plus is decreasing and Fc plus is increasing, and at this point where there is a peak, both of them will become same. So concentration will become 50% by 50%, and the log of this quantity will become 1, because 1 by 1 or 50 by 50. So concentration of A and concentration of B becomes same, and this quantity becomes 0, which means E becomes E naught. That means at this particular point E becomes E naught. And what is this E naught? E naught is the standard potential. So this is how we can find the standard redox potential of the material. Now here there's a graph given. This is the amount, the green represent the amount of Fc, and the blue represent the amount of Fc plus in the electrolyte. This is very important. This is in the electrolyte near the electrode. Near the electrode means somewhere here. This is the point near the electrode. So this is the this is where the electrode is present, and the distance from electrode is measured in this way. So at point A, this is point A mentioned here, this is the point A, and at this point A, the Fc plus is concentration, Fc plus concentration is almost equal to 1, which means it is 100% of Fc plus, and there is no Fc present at the electrode surface. So Fc is 0 here. Okay, this is the starting point of our potential CV curve. So there is no Fc plus, and there is only Fc plus present. That is why the concentration is 1. The concentration of Fc plus versus Fc relative to the distance from the surface of the electrode are dependent on the potential applied and how species move between the surface of the electrode and the bulk of the solution. Now this is just the concentration variation given in Fc and the Fc plus uh, relative to the distance from the surface of the electrode. That means from the surface of this electrode, the concentration of Fc and Fc plus depends on the potential applied, and it also depends on how species move between the surface of the electrode and bulk of the solution. Now this means that this is the area where there is bulk material is present. This is the electrolyte. Now this electrolyte, here on the surface there will be Fc and Fc plus ions on the surface and near the surface. That means just near a small distance from the surface of the electrode there will be Fc and Fc plus. Now once this Fc get reduced, Fc plus get reduced to Fc, that means when Fc plus get reduced by accepting electron to Fc, the amount of Fc increases, amount of Fc here increases, and this Fc plus will come down and Fc will increase, and this concentration depends on the potential applied and also on the movement of species. How well, this simply means the ionic conductivity of the material, how well the electrolyte is able to provide the conductivity to the Fc plus ions. Okay, now as the potential is scanned negatively, this is further in going towards the 0.3. We have reached up to C, and on further increase to D, the Fc plus get steadily depleted near the electrode. That means the Fc plus will become nearly zero, and and almost everything will be converted to Fc, and at the point C where there is the peak cathodic current, so this is called cathodic, means it is reduction occurring. Okay, the cathodic peak is observed and the current is dictated by the delivery of additional Fc plus ions by diffusion from the bulk solution. Now what is this happening? The further Fc plus get reduced to EFC, and thus from where this Fc plus is coming, this Fc plus is coming from the bulk material. There is a transport of Fc plus ions towards the electrode. So here, if I consider this as the bulk material, from somewhere very far from the electrode, the Fc plus gets moved towards this electrode, and this transfer is called mass transfer, and the process is called diffusion, because diffusion occurs from higher concentration to lower concentration. These are the reason for the movement of Fc plus ion towards the electrode. That is, here there will be more concentration of Fc plus. Here near the electrode, Fc plus is reduction. So here is higher concentration to lower concentration. This mass transfer mainly occurs due to diffusion. Now further, when you increase the potential to 0.3, there is a reduction in current. Now this reduction in current, even though there are Fc plus ions present, there is a reduction in current. This is due to the resistance offered resistance offered by the bulk material. Resistance offered by the bulk material. So once the resistance is high, the current will come down, and there is also a formation of uh, on the electrode. There is FC formation. There is so it will be difficult for the Fc plus ions to get attracted or to attach to the electron which is being present on the surface due to the increased negativity, okay, negative potential. So Fc plus ions will find it difficult to reach the electron, so thereby there is a reduction in current. So this is what happens from C to D. Yeah, here this description is regarding the formation of the layer and the transport. So what is it saying? That the volume of the solution at the surface of the electrode containing Fc. So if you consider this electrode, so electrode will have electrons on the surface because we are giving the negative charge, and this Fc plus ions will go and get attached, which becomes Fc over here. So after reducing to Fc, here you will have Fc ions, sorry, Fc atoms, which is attached to the electrode. Now this is called the diffusion layer. Now as and when you increase the potential, that means more and more electrons are on the surface, and this continues to grow throughout the scan from A to D, the diffusion layer keeps increasing. Now, and once it increases, this slows down the mass transport of Fc plus to the electrode. Now what does this mean? So furthermore, when more electrons are being produced or is attached on the surface, further Fc plus cannot go and get attached. It hinders the further reduction, that means there is a reduction in redox reaction. I mean reduction in reduction. Okay, so that means there is lesser current because transport or the transfer of ions is not happening. So there is reduction in the current. That is why there is a decrease in current from C to D. Now thus is a conclusion. Upon scanning for to more negative potential, the rate of diffusion of Fc plus from the bulk of the solution, that is from the bulk, this is where the bulk is, from the bulk of the solution to the electrode surface becomes slower. Now slower means the rate is less, lower rate. Current is nothing but the rate of change of charge Q. So when the rate of diffusion means charge transfer reduces, the current also will reduce. So resulting decrease in the current as scan continues from C to D. So this is explanation why there is a shape like this. This is called the beak of the duck. So this is a duck shape, and this is represent the beak. Now here in the graph you can see this is the amount of EFC plus, and this is the EFC. So it near the electrode, so this, let us call this as the very near to the electrode. Very near to the electrode, the amount of EFC is increasing, while the amount of Fc plus is decreasing near the electrolyte, so it's going in this direction. So this is okay. Now and as it move away from the electrode, it increases. That means Fc plus increases and Fc decreases as it moves away from the electrode. Now that is at the point C, where you have the peak current and the corresponding voltage at the peak is called EPC. And at D, when it reaches D, you can see almost all Fc plus ions have converted to Fc. So you look at this near the electrode. Let us say this is the nearest region around the electrode. So if you consider this as the electrode, then over here the most of the particle, that means on the surface, near to the surface, Fc is high. That means almost all particle are Fc only, because it is on the surface, it is attached, and as it increases, moves away, Fc plus increases in this direction. Okay. And yes, this is the explanation to the duck shape of the cyclic voltammetry. Now let us see what happens when you reach the point D. D is called the complete sweep from the negative potential to the positive potential, negative to the positive. Now in the next cycle we will see how it moves from positive to negative. What happens when it moves from D to G. Now as mentioned, when the switching potential D is reached, that means this is reached, the scan direction is reversed from minus 0.3 to plus 0.3. So when the potential is scanned in that positive direction, that means from minus to positive, in the positive direction, where it is called anodic, the concentration of Fc plus at the electrode surface get depleted. So earlier when the negative cycle was happening, then there were Fc atoms on the surface of the electrode, and when there is a positive potential being applied here, the electron will be attracted towards this electrode. So electron will be attracting, so it has to lose, that means the Fc has to lose the electron, and after losing it has to come to the bulk of the solution and to become Fc plus. And once it loses electron, it cannot remain as a solid, it will be in the ionic form. So as more and more potential is being applied, the Fc plus, more number of Fc plus ions get into the bulk of the solutions, and at a point you will see the amount of Fc plus ions will be reaching the amount of Fc. So at that particular point you reach the F, where you have the anodic peak at F. So at F we have anodic peak. Now so Fc plus ions at the electrode surface get depleted, and concentration of Fc at the electrode surface get increased. So this Fc, yeah, satisfying the Nernst equation. So this is the Nernst equation as we have seen in the case of the negative cycle, that is the reduction cycle. This is oxidation, where electron is being released by the Fc. So at E and F, Here we have the this is EFC plus, this is EFC. So EFC plus starts to decrease near the bulk, near the electrode. So let us consider this is the near the electrode region, and near the electrode region FC plus starts to decrease. See here, it's FC plus starts to decrease, and similarly the EFC gets increased near the electrode, and after that it decreases, because in the bulk there is no EFC. Similarly, on further increase, the EFC plus further get reduced. So this is EFC plus, this is EFC. So it reaches somewhere, it does not actually what completely get reduced to zero, because some residual EFC atoms remain. So here we have the peak, and this is IPC, which represent this cathodic peak, and IPA represent the anodic peak. So that's it. Here in the cyclic voltammetry you have got two peaks, one representing IPC cathodic, where FC plus get reduced, and IAC, where this is anodic peak, where EFC becomes EFC plus oxidized, and the peak IPC, it corresponds to a potential at for example this at C. So EC and IAC, this is potential corresponding to the F, that means the reduction and oxidation peaks. Now E half is equal to EC plus EF by 2, or also write the cathodic and oxidation and reduction peaks voltage by 2, and this is the standard redox potential. Redox potential of the material.